Hello, welcome to Understanding Power Electronics. There are two ways of normalizing a DC-DC converter's equations. One is by basing the normalization on the input DC voltage and the other by basing it on the output DC voltage. In this series of videos, we have called them as base V in method and base V naught method. In this video, we will go through both of these methods as applied to a buck step-down DC-DC converter. We will also see under what conditions each of these methods may be useful. That's our aim. Let's get started. First, we will see the base V-in normalization. In base V-in, we use the input voltage V-in as the normalizing factor for voltage. That's an obvious thing to do. You're feeding some input voltage, so you know the input voltage. Let's use that as the normalizing factor. Buck converter has two modes of operation: continuous conduction mode or CCM and discontinuous conduction mode or DCM. In continuous conduction mode, the inductor current always stays above zero. In discontinuous conduction mode, the inductor current comes and touches zero and stays at zero for some interval called the discontinuous interval. In CCM, the buck converter has two intervals of operation in one switching cycle, one when the switch is on and it is conducting, and the other when the switch is off and the diode is conducting. In discontinuous conduction mode, there are three intervals of operation. One when the switch is on and it is conducting, and another when the switch is off and the diode is conducting, and the third one when the switch is off and the diode is also off. In between the continuous conduction mode and the discontinuous conduction mode, the converter goes through a boundary operation. At the boundary, the inductor current just touches zero and immediately the switch is switched on again. At the boundary, both the CCM output voltage equation and the DCM output voltage equation will be valid. Next, we will see the unnormalized equations of the buck converter. Under CCM, output voltage V naught equals duty cycle D times V in, the input DC voltage. Given input voltage, the output voltage depends only on the duty cycle and not on the output current. Let us reduce the output current. As we reduce the output current, the operation will reach boundary current operation at some particular output current. That boundary current equation is given by IOB, the output boundary current value, equals V in Ts by 2L times D times 1 minus T. So if the output current is more than this boundary current, then the operation will be in continuous conduction mode. If it is less than this boundary current, the operation will be in discontinuous conduction mode. Again, as I said, at the boundary operation, the output voltage equation for CCM will be satisfied. The output voltage equation for DCM will be satisfied. So V naught will be still dV in. If we reduce the current even more, then the operation enters discontinuous mode and the output voltage is given by V naught equals D squared by D squared plus I naught by V in Ts by 2L times V in. Here you notice that the output voltage depends on the input voltage, the duty cycle, the output current, and even the frequency or the switching period and the inductor value. So these three put together is the complete DC characteristics of the converter in equation form under steady state, assuming ideal operation. Now we will normalize this using base V in normalization. The base V in normalization, we have gone through it in detail in another video in this series. Here I am going through it again so that you can find both the normalization methods, their descriptions, characteristics of the converter using those normalization all in one place. When we look at these equations, base V in normalizations become clear. The voltage normalization factor, as I mentioned, is V in. Vn equals V in. Vn voltage normalization factor, or the base value for voltage, is V in. In, the current normalization factor, or the base value for current, is V in Ts by 2L. The voltages and currents in the circuit will be divided by these factors. First, let's take the CCM equation. V in, you can bring it to the left hand side. V in is the voltage normalization factor. So V0 by V in is V0 by Vn, which is the normalized output voltage. So VON is VO by Vn, that is VO by Vin, that will be D, the duty cycle. Once you normalize, the variables become dimensionless. VON is dimensionless. There are no units. Taking the boundary current, V in Ts by 2L is on the right hand side. You can shift it to the left hand side. IOB by V in Ts by 2L is IOBN. That is the normalized boundary current. So the normalized boundary current IOBN is IOB by IN or IOB by VNTS by 2L, and that is D times 1 minus D. Again, IOBN is dimensionless. Since V0 is equal to dV in, here also V0N is D. V0N is VO by Vn, which is VO by Vin equals D. So I can substitute for D VON, and the normalized boundary current IOBN can also be written as VON times 1 minus VON. Lastly, we will take the DCM equation. We can bring the V in to the left hand side. So VO by Vn will become VON, the normalized output voltage. IO by V in Ts by 2L is ION, the normalized output current. So the normalized output voltage VON equals D square by D square plus ION. So these three equations, VON equal to D, IOBN equal to D times 1 minus D, and VON equal to D square by D square plus ION. These three define the complete operation of the converter using normalized equations. Next, we will plot these normalized equations. Again, these are the base V in normalizing factors. Vn equals V in, In equals V in Ts by 2L. We will plot the normalized output voltage VON with respect to normalized output current ION. D will be the parameter. First, we will plot the boundary. IOBN equals VON times 1 minus VON. Remember, IOBN is also an output current under a particular condition, boundary condition. This gives an equation between VON and IOBN. We can plot this here. That will be a parabola. When the output current is more than this value, the operation will be in CCM. When the output current is less than this value, the operation will be in DCM. Here at this point, the boundary current is maximum. We can take the boundary equation, differentiate it, set it equal to 0 and find the maximum point. We can show that will occur when D is equal to 0.5 or VON equal to 0.5. Remember, VON equals D at the boundary also, and the corresponding ION is 0.25. Next, we will see the CCM operation. VON equals D. If you take a particular value of D, D is constant. So VON is some constant. The output voltage VON does not depend on current. So VON equal to D will be a horizontal straight line. We can plot this. This blue line corresponds to D equal to 0.1, VON equal to D equal to 0.1. The straight line will not continue inside the boundary curve. We can plot in a similar way for d equal to 0.2 and 0.3. Again, you notice that the characteristic is straight line and it does not extend into the DCM region. You can then plot 0.4, 0.5, 0.6, etc. up to d equal to 0.9. Next, we will plot the DCM voltage curve. We will start with d equal to 0.1. When ION is equal to IOBN corresponding to d equal to 0.1, at that boundary, this equation also should be satisfied. So VON should be equal to zero point 0.1. Please check it out and see for yourself if it is true. If you have any questions or comment on it, please post it in the comment section. As ION reduces, the denominator will reduce. As denominator reduces, VON will increase. So the output voltage will increase. That's what happens here. As ION goes towards 0, VON goes towards d square by d square, that is 1. So the output voltage will tend to go towards the input voltage value as the current is reduced. I can plot in a similar way for d equal to 0.2, 0.3, 0.4, etc. So this is the complete DC characteristics of the converter in graphical form using base V in normalization. We'll quickly see how to use this graph. Here's an operating point marked on the characteristics. The duty cycle corresponding to this operating point is 0.4, ION is 0.45, and VON is 0.4. The operation is in continuous conduction mode. If you assume that Vn, that is the base voltage for normalization, is 100 volts and In, the base current for normalization, is 10 amperes, then the actual IO is 4.5 amperes and the actual output voltage is 40 volts. Now let us reduce the load current. As we reduce the load current, at a particular point, the operation will reach the boundary operation that is shown here. ION corresponding to that is 0.24. You can verify it using the boundary equation. The duty cycle is still 0.4 and the normalized output voltage is still 0.4. That means the actual output current is 2.4 amperes at the boundary operation and the output voltage will be 40 volts. Now we reduce the load current even more. As we reduce the load current even more, the operating duty cycle remains at d equal to 0.4. So that means we are on this green curve and the load current is reduced. So ION will be reduced and we reach this operating point. At this operating point, ION is 0.1067 and VON is 0.6. The corresponding current is 1.067 amperes and the corresponding voltage is 60 volts. That means as the current is reduced to 1.067 amperes, the output voltage will increase to 60 volts. So overall, we can notice that the regulation becomes poor when you enter the discontinuous conduction mode region. That's how this curve can make the operation of the buck converter clearer to us. Notice that we have assumed Vin is constant. This normalization is useful when Vin is constant. Suppose Vin changes. When Vin changes, of course the base voltage will change. That is to be expected. But the base current also changes. Consider the operating point here. The normalized current is 0.45, but that is assuming a base current of 10 amperes. If Vin changes and the 10 amperes becomes 12 amperes, 15 amperes, then ION will change even when the actual current does not change. As Vin changes, the normalized output current will change. So it's not convenient to use this normalization if Vin is changing. So base V in normalization is useful in understanding so-called open loop operation of the converter with V in being constant. That means we are not trying to control the output voltage, the input voltage V in is constant. It is useful in making us understand the basic property of the converter. A fixed voltage, the load current is varying. For a particular duty cycle, how does the output voltage vary? So what is the basic property of the converter? This normalization is useful for that purpose. Next, we will see base V0 normalization. In many applications, the output voltage V0 will be maintained constant in power supply applications, for example. So what we are doing here is making sure the output voltage V0 remains constant when the load is varying and when the input voltage is varying. So as the input voltage varies, as the load varies, the duty cycle is constantly adjusted so that the output voltage will be maintained at some desired value. This is achieved through closed loop control of the output voltage. This is a load that requires a voltage V0, and this is some DC source V in, which is not constant. V in is not a constant value, it can vary. So in between the source and the load, we use a DC-DC power converter. There are two things that can affect the DC-DC power converter. The load current that is drawn by the load and the input voltage that is applied to the converter. When either of them vary, output voltage V0 is still to be maintained. In order to achieve it, first we sense the output voltage. Here, VOS is a signal voltage proportional to the output voltage V0. A simple voltage sensor made of a potential divider arrangement is shown here. You can use other arrangements also. For example, you can use a Hall effect based sensor. This output voltage signal VOS is compared with the reference VO reference and an error signal is obtained. A controller is typically used which produces a VC control voltage which will depend on the error signal. The control voltage is then fed to a pulse width modulator which produces the duty cycle pulses D depending on the value of the VC. Usually the relationship between the pulse width and the VC will be linear, but it doesn't have to be. If VC increases, the duty cycle will increase, the pulse width will increase. If VC reduces, duty cycle or the pulse width will go down. The frequency of the switching is determined by an oscillator inside the pulse width modulator. These pulses have to be fed to the switch inside the DC-DC power converter. So a driver is used to make these pulses suitable for the switch. Switch may require higher current. It may require a particular voltage, or the switch may require the voltage level to be shifted or an isolation to be introduced. Whatever it is, the driver takes care of it. But the frequency, the pulse on interval duration, off interval duration, those things are decided by the pulse width modulator. Supposing this is operating and V0 goes above the output voltage desired, then VOS will go up. When VOS goes up, the error will come down. Because the error is VO reference minus VOS, error will come down. As the error comes down, we see the control voltage comes down. As the control voltage comes down, the pulse width will be reduced, duty cycle is brought down, and the output voltage is brought down. So also, if the output voltage goes down, the reverse happens, and the duty cycle is now increased, the pulse width is increased until the output voltage reaches V0 desired. You can implement this control loop either using analog circuits or digital methods. Under this condition, the output voltage will remain constant. In applications where this is happening, it makes sense to make the normalization based on the output voltage V0. Next, we will see the base V0 normalization. This is the buck converter again. These are the normalized equations. We saw them before. Vn, the normalizing factor for voltage, is V0. In, the normalizing factor for current, is V0 times Ts by 2L. Notice that the current normalizing factor is now V0 Ts by 2L and not Vin Ts by 2L. Also notice that we have used capital N for the subscript to differentiate this normalization from the earlier base Vin normalization. Now we will do the normalization. First take the CCM equation. V0 now is the normalizing factor. So what we can normalize and what we will normalize is the input voltage. So Vn, the normalized input voltage, is Vn divided by Vn, the normalizing voltage factor. So that is Vn by V0, and Vn by V0 is 1 over d. V0 by Vn is d, so Vn by V0 is 1 over d. So this is the normalized CCM equation, Vn equals 1 by d. Next, we will take the boundary equation. I naught b is V in Ts by 2L d times 1 minus d. V in d is V0. So we can rewrite this equation as V0 Ts by 2L times 1 minus d. And V0 Ts by 2L is the current normalization factor. So IOBN, the normalized boundary current, is IOB by IN or IOB by Ts V0 by 2L, and that would be equal to 1 minus d. So IOBN is 1 minus d and 1 by d is V in n, and we can rewrite it as IOBN equals 1 minus 1 by V in n. So these two equations were pretty straightforward, pretty easy to recast them as base V0 equations. The DCM equation, to normalize, it will take a bit of manipulation. We will do that next. This is the DCM equation, V0 equals d squared by d squared plus I0 by V in Ts by 2L times Vn. We can bring this denominator term to the left hand side. So d squared plus I0 by V in Ts by 2L whole times V0, that will be equal to d squared Vn. So this d squared V0, I can take it to the right hand side and combine it with the d squared Vn already there. Then the left hand side, what will remain is I0 V0 by V in Ts by 2L, and that will be equal to d squared times Vn minus V0. On the right hand side, let us pull the V0 out. On the left hand side, on the denominator, we are having V in Ts by 2L. Multiply and divide that by V0. Okay, we are doing two things. On the right hand side, just pull the V0 out. On the left hand side, in the denominator, you have V in Ts by 2L. Multiply and divide that by V0. When you do this, I0 V0 divided by V0 Ts by 2L times Vn by V0. Notice that I have multiplied by V0 and divided it by V0 here. That will be equal to V0 d squared within brackets Vn by V0 minus 1. V0 and V0 will cancel. We have got close to the normalized equation already. So I will take this Vn by V0 to the right hand side. So I can rewrite this equation as I0 by V0 Ts by 2L equals d squared times Vn by V0 times Vn by V0 minus 1. Vn by V0 is Vn. I0 by V0 Ts by 2L is ION. So this equation can be rewritten as ION equals d square times V in n times V in n minus 1. That is the normalized equation using base V naught normalization. We can rewrite this in alternate forms depending on how we intend to use this equation. This is the equation we just now derived. This equation is an equation for normalized output current. The normalized output current is on the left-hand side. We can rewrite this equation so that the duty cycle is on the left-hand side. So that is simple to write. You just solve for d square and then take the square root. If you do that, you will get d equals square root of ION by V in n times V in n minus 1. So 1 and 2 equations are the same equation in two different forms. We can also rewrite this equation so that V in n is the subject of the equation. V in n is on the left-hand side. I can take equation 1, expand the right-hand side, and then combine that with ION from the left-hand side. And I can rewrite that equation as follows. D squared V in n square minus d squared V in n minus ION equals 0. Please work it out and convince yourself that you can rewrite it in this form. You can recognize a quadratic here. This is a quadratic in terms of V in n. If you have a quadratic equation, ax square plus bx plus c equals 0, you know that the solution x will be minus b plus or minus square root of b squared minus 4ac by 2a. Here a is d square, b is minus d square, c is minus ION, and x is v in n. So you have to plug in those things and you can solve for v in n. V in n is d square plus or minus square root of d power 4 plus 4d squared ION by 2d square. Please work it out yourself and verify that this is correct. Now I can divide this part and this part by 2d square and I will get this. D square by 2d square is 1 by 2. And here I have taken 2d squared inside, so it becomes 4d power 4. So this will be half plus or minus square root of 1 by 4 plus ION by d square. Notice that I have this plus or minus sign here. V in n is V in divided by VO. VO is always less than Vin. It's a buck converter. So V in n will always be more than 1. We are not going to achieve it by taking the minus sign. So you reach the correct solution only by taking the plus sign. So V in n will be half plus square root of 1/4 plus ION by d squared. So this is the third form. So you have three different forms of the equation. One for ION, one for D, one for V in n. In the first form, given D and V in n, you can find out what is the normalized output current. In the second form, given ION and V in n, you can find out what is the duty cycle. In the third form, given ION and D, you can calculate what is the normalized input voltage. As I mentioned, at the boundary operation, both the CCM output voltage equation and DCM output voltage equation are valid. Here, using base V naught, please show that equation 3, this equation, reduces to V in n equal to 1 by D, that is the CCM equation, at boundary current ION equals IOBN equals 1 minus D. Please do that and post it in the comment section. Next, we will plot the complete DC characteristics of the converter using these base V naught normalized equations. The normalizing factors are Vn equals V0 and In equals V0 Ts by 2L. The normalized equations we just now saw, the CCM equation is V in N, normalized input voltage, equals 1 by D. IOBN, normalized boundary current, equals 1 minus D, and is also same as 1 minus 1 by V in N. The normalized DCM voltage equation is V in N equals half plus square root of 1/4 plus ION by D square. So what are we going to plot here? X-axis is clear, ION, I0 divided by V0 Ts by 2L, that is the normalized output current. Y-axis, we would like to have V0 by Vin, which is the familiar voltage gain of the converter. Then it will become a voltage gain versus output current plot. And that V0 by Vin is 1 over V in N. V in N is Vin by V0. So V0 by Vin is 1 over V in N. So we will plot 1 over V in N and I0 N. I'm taking y equals 1 over V in N. So we will rewrite these equations in terms of 1 over V in N so as to facilitate the plots. If you take the CCM equation, V in N is 1 over D, so 1 over V in N is D. Then if you take the boundary current, CCM, DCM boundary, IOBN equals 1 minus 1 by V in N. 1 minus 1 by V in N is 1 minus Y. So I can rewrite it as Y equals 1 minus IOBN. Then the last one, the DCM equation will be Y equals 1 over V in N, which will be 1 over this thing on the right hand side. So that will be 1 over half plus square root of 1/4 plus ION by D square. So we are going to plot these three equations. Y equal to D, Y equal to 1 minus IOBN, and Y equal to this term on the right hand side. First let's plot the boundary equation. It's a straight line. It's not a parabola, it's a straight line. When IOBN equal to 0, Y will be equal to 1. When IOBN equals 1, Y will be 0. It's just a straight line. On the right hand side, ION is greater than the IOBN. There the operation is in CCM. On the left hand side, ION is less than the boundary current. There the operation is in DCM. We will plot here the CCM characteristics and the DCM characteristics together at one go. So here I have plotted the CCM characteristics and DCM characteristics for D equal to 0.1. So under CCM, until you reach the boundary, Y is constant, V0 by Vn is constant. Y is D, D is equal to 0.1, so V0 by Vn is 0.1. This plot is made using this DCM equation. Here you can see that as ION becomes smaller, the denominator becomes smaller and Y will increase. Y is V0 by Vn, so V0 by Vn will increase. And when ION becomes 0 or goes close to 0, the term under the square root will go towards 1 by 4. So square root of 1 by 4 is half. So Y will tend towards 1. That means V0 will tend towards Vin as ION tends to 0. We should get the same result as before because the converter is the same. It is just different ways of doing the normalization. This is the plot for D equal to 0.1. You can then do the plot for D equal to 0.2. So you can see that in the CCM region, it is a horizontal line. Y 1 over V in N will be equal to 0.2. And In the DCM region, the normalized voltage quickly rises and goes towards 1. Likewise, you can plot D equal to zero point 0.3. You can plot D equal to 0 0.4, 0 0.5, and so on. So this is the complete characteristics of the buck converter using base V0 normalization. Next, we will see how these characteristics based on V0 normalization can be useful in visualizing and understanding the converter operation under steady state when the output voltage is regulated. That is, when V0 is held constant. This is the buck converter. Here we are showing one operating point of the converter. The duty cycle is 0.3. The operation is under CCM because the point is located on the CCM region. The normalized output current is 1.5 and 1 over V in N is 0.3. Remember, we have called 1 over V in N as Y, that equals V0 by V in. So V0 by V in is 0.3. Under continuous connection mode, of course, V0 by V in will be equal to D. As an illustration, let's assume Vn, the normalizing voltage, is 30 volts. That means the output voltage is 30 volts. And In, the normalizing factor for current, is 10 amperes. The input voltage will be 100 volts. 100 times 0.3 will be 30 volts. And the output current will be 15 amperes, 1.5 times 10. Since 1 over V in N is 0.3, V in N is 1 by 0.3 or 3.333. Now let's change V in. Let's assume that we are reducing V in. As we reduce V in by V0 ratio will go down. So 1 over V in N or Y will go up. Let's say Y value changes to 0.6. That means V0 by V in has changed to 0.6. The operation changes to a duty cycle of 0.6. So as the input voltage is changed, the system adjusts the duty cycle from 0.3 to 0.6 so that the output voltage under steady state remains the same. So under constant current, when the voltage changes, the operating point shifts vertically. The new operating point, V in is 50 volts, V0 is again 30 volts, duty cycle is 0.6 and the current is again 15 amperes. So we can see the effect of changing the input voltage on this graph under constant output voltage conditions. Now let's bring the operating point back to where we started from. ION is 1.5, Y equals 1 over V in N is 0.3, duty cycle is 0.3. Now keeping the input voltage constant, let's reduce the output current or the load current. As we reduce the load current, the operating point will shift to the left towards the CCM-DCM boundary. At some current, it's going to hit the boundary, it's going to operate under boundary condition. Let's show that. So at the boundary, we are keeping the output voltage constant. We have not changed the input voltage. So Y V0 by V in remains the same. The corresponding normalized boundary current is 0.7. The actual boundary current will be 0.7 times 10 amperes. That will be 7 amperes. Now let us reduce the output current still further. Remember, we are keeping the output voltage constant. We are now not changing the input voltage also. We are only changing the output current. So the operating point will move horizontally leftwards deeper into DCM. We will show that here. So the operating point now shifts to the dark green curve. At this point, the normalized output current is 0.311 or the actual current is 3.11 ampere. The output voltage is still 30 volts. So even in DCM, we are managing to keep the output voltage at 30 volts. So how are we doing it? By changing the duty cycle. So We are now operating on the green curve, and the green curve corresponds to D equal to 0.2. Under DCM, the output voltage has a tendency to go up. We are pulling it back by dropping the duty cycle from 0.3 to 0.2 in this case. So we are able to see how the output voltage is maintained by changing the duty cycle. So under closed loop condition, when we are regulating the output voltage to be constant against input voltage variations, against load current variations, base V0 normalization and this way of representing the DC characteristics of the converter, they are useful. They are useful in understanding how the converter operates. There are many such applications where the output voltage is held constant. So this is a useful way of representing or showing the DC characteristics of the buck converter. With this, we have come to the end of this video. In this video, we saw two ways to normalize the equations of a buck step-down DC-DC converter. One is base V in normalization. Here, we used the input voltage as the voltage normalizing factor. This is useful in understanding the open loop operation or the basic operation of the converter, where we apply a constant DC input voltage and then vary the load current for a given duty cycle. We saw in detail the base V0 normalization. In base V0 normalization, we use the output voltage V0 as the voltage normalizing factor. As we saw, this is useful under closed loop conditions when the output voltage is kept constant against input voltage variation and load variations. We have come to the end of this video. If you find this video and this series of videos useful and interesting to you, please consider subscribing to this channel and clicking the like button. Thank you.